All right, so here's the hope. If you are watching this video, you have looked at the Lesson 18 worksheet. You have worked through those questions on your own. You have answers. They may not be great. You think they're decent. Maybe you were a little bit stuck on the integration question toward the bottom of the front side, but you at least have ideas about how those things would play out, why series matter, stuff like that. Um, in this video, I want to talk about some of the key questions there and why the front side is so important. Then there will be a different video for some other things that I'd like to talk about in this lesson. Okay? Okay. So in particular, I would like to play with the idea that a of xy is a of x plus a of y. And in this case, x and y are positive real numbers. I want to drive home why that is, in fact, true. So we should understand that the end goal is to show that the integral from 1 to xy of 1 over t dt is the integral from 1 to x of 1 over t dt plus the integral from 1 to y of 1 over t dt. That's the goal. If we can get here, this is the same as that. So this is the statement we're trying to prove. How do we do that? You ask good questions. So let's do this. Let's begin with a notion that is very Calc 1. When you have an integral from 1 to xy, that's the integral from 1 to plus the integral of to xy. And we can choose any number we like to fill in that gap as long as this is the same as that. And so the number we're going to choose is x. And now you're thinking 2 out of 3 ain't bad, right, Meatloaf? Like this matches. So you're like, hey, 2 out of 3 ain't bad. So I guess what we've got to show is that this integral is the same as this integral. And the secret here was a u substitution, something you are again familiar with from Calculus 1 all those many, many years ago. One moment, please. All right, so what was that u substitution? That u substitution said let u equal 1 over x times t. Remember, x is just a number. It's a positive real number. T is the variable of integration here. So if u is 1 over x times t, then du is 1 over x times dt, right? Like we need to make this substitution. So this integral over here, we're going to leave everything else exactly the same. This integral is the integral of, okay, so 1 over t, so t is x times u, right? Now 1 over x is a number because x is a number. U is going to be the variable of integration. dt is x du. Well, this is looking very promising. Then we do a complete change of variable. These are t limits. We want to get rid of everything that smells like t and replace it with something that smells like u. If t is x, then u is 1. And if t is xy, then u is y. Oh, that's looking very nice. because this integral very clearly has the same value that that integral has, because the integral of 1 over u du is the same as the integral of 1 over t dt. And so we start with a result from Calc 1. We do a u substitution from Calc 1. We recognize that a dummy variable is a dummy variable is a dummy variable, and we get the result that we need. So for our function capital A of xy is a of x plus a of y, and that's a big deal. That is a big deal because of the following theorem. We're going to let alpha be a positive real number not equal to 1 if some function from the positive real numbers to the entire real numbers is a continuous function satisfying f of 1 is 0, f of alpha is 1, and f of xy is f of x plus f of y for all x and y in the domain. Then f of x must be the log function with a base of alpha for all x in the domain. You established in the worksheet that capital A satisfies this and capital A satisfies this, and we just established that capital A satisfies this. So the key is to prove that this theorem is true, and that will establish that capital A is in fact the log function. Here's our idea. We will show that f of alpha to the gamma is gamma for all real gamma. Think for a moment about why doing this establishes that our function has to be the log function. Okay, so let's do it. So we play the game first for positive integers. If m is a positive integer, what is f of alpha to the m? Well, if m is a positive integer, then alpha to the m is alpha times alpha times alpha until there are m copies of alpha. And we know that f of a product becomes a sum of function values. So this is f of alpha plus f of alpha until there are how many copies of f of alpha? M copies of f of alpha. But f of alpha is 1. So if m is a positive integer, then what we want, we get. Now, let r, what is slowing me down? Let r be a positive rational number with r equal to m over n, and we're just going to say out loud, because it's a video, m and n are integers, n is not 0, m over n is in the lowest terms. Then m, which is f of alpha to the m, is f of alpha to the r to the n, right? Alpha to the m over n to the n, equality is preserved. Well, how do we get this? N is a positive integer. And because n is a positive integer, this tells us that this is n times f of alpha to the r. And if this is equal to that, then f of alpha to the r is m over n. I should note that the results are similar if m is a negative integer here, and if r is a negative rational number here. All the integers, all the rational numbers obey this. It's just easier to see with positive integers and positive rational numbers. Now, take a sequence r sub n. Let it be a sequence of rational numbers converging to gamma, which is some real number. So here's what we do. F of alpha to the gamma. So what do we know? We know that the sequence of rational numbers converges to gamma. So we know that gamma is the limit as n approaches infinity of the r sub n's. We know that. Now, we know that the exponential function is continuous. And because the exponential function is continuous, alpha to the limit of the r sub n's is the same as the limit of the alpha to the r sub n's. That comes because the exponential function is continuous for all real numbers. Well, we also know that f is continuous. We assumed that way up here. F is a continuous function. And because f is a continuous function, f of the limit is the limit of f. Well now, f of alpha to a rational number is just that rational number, because we established that for rational numbers, this held true. And that limit is gamma as needed. We needed f of alpha to the gamma to be gamma for all real numbers. We've got that. We are done. Well, I guess we're sort of done. There's a thing that we need to do. Our f needs to be a continuous function. Was capital A continuous function? That's a legitimate question. Is capital A continuous function? If it's continuous, then it satisfies all of the properties that are necessary for that theorem to hold true, and then this is in fact the log function. But of course we know that this is continuous because we know that it has a derivative, and functions that are differentiable are continuous. So alpha is a log function with some base. What's that base? Well, we can do area estimates. We can use the intermediate value theorem. Alpha does turn out to be E. A of x is in fact the log function that you are familiar with. Okay? Okay? Cool. In the next video, we'll talk about how to motivate E for teenagers using some stuff that you know from calculus. But that'll be in a separate video because you've gone 15 minutes and so you need a cup of coffee or a bathroom break. Okay, bye.